This is 22nd lecture and we continue our problem solving on Fourier transforms, discrete Fourier transform and Z transform. The problem that we start with is 3.92 and the statement of the problem is, let x of z be equal to Z transform of x of n, and x of n is of length 12 starting at n equal to 0. That is, we have x0, x1 up to x11. Okay. Let x0 of k be equal to x of z with z equal to e to the j 2 pi k divided by 9. All kinds of complications. K going from 0 to 8. Determine, what does this mean? This means a 9-point DFT. Okay, 2 pi by 9 and therefore it is a 9-point DFT. The question is, but the sequence length is 12, right? So, length 12 sequence, first you have taken the Z transform, then Z transform is sampled on the unit circle, 9 samples. That can be done, I mean no harm, but the problem is determine the 9-point IDFT of IDFT x0n of x0k, that is invert this IDFT. The problem is without computing the latter function. You must not compute x0k, the latter function. One of the important things that I now have an opportunity to point out is, why didn't we write x of k here? Why did we use a subscript x0? X of k would be the same as x of z with z replaced by k, whereas x0 of k is the DFT. It is a different function altogether. You must distinguish between them. Many textbooks even do not distinguish this, they make a mistake, which is not correct. All right. To understand the problem, we have taken x of z, the Z transform of a finite length sequence. Then we have taken, for the same sequence, we have taken the DFT, but we have not computed the DFT. What we have done is x of z we have sampled on the unit circle at 9 points. So, we have taken 9-point DFT. You now have to invert the DFT. Naturally, you shall not get x of n, because this was 12 point and this is 9 point. So, you get a different x1 of n, that is why x0 of n, but you must do this without computing x0 of k, which means that we have to appeal to the basics. The basics are that x of z is equal to x of n, z to the minus n, the n equal to 0 to upper limit 11. So, x0 of k is equal to n equal to 0 to 11. These limits remain the same because x of n remains the same. Only z changes, z to the minus n becomes e to the minus j 2 pi n k divided by 9. I have to compute x0 of n, and this is the point where one has to understand. We take an IDFT, in other words we write the IDFT relationship. Let us see what happens. I am not allowed to compute x0 of k, so I will not compute. Let us see what is IDFT. IDFT would be 1 by 9 point summation k equal to 0 to 8 x 0 of k e to the power j 2 pi n k divided by 9. Okay. And then the trick is, I have not computed x 0 k, but I can substitute this relationship. So, I substitute, but then in substitution you must change the dummy variable, otherwise you run into problem. You must not have j 2 pi n k, you must change the variable here. So, I write this as 1 by n summation k equal to 0 to 8 summation for x 0 k, let us write it as r, x of r equal to 0 to 11. If you want, you put a bracket here, okay, e to the power minus j 2 pi r k divided by 9 multiplied by e to the j 2 pi n k divided by 9. Okay. Then we interchange the usual trick that we do, interchange the two summations. So, we write x 0 of n as equal to 1 9 summation r equal to 0 to 11 x of r, then summation over k 0 to 8 e to the power j 2 pi n minus r k divided by 9. And this function as you know is equal to 9 if r is equal to n. Not just that, you see the number of, this is the point to be understood clearly. Number of points here is 9, but the number of points in x is 11, and therefore this is equal to 9 if r is equal to n. Not only that, if small n is increased by capital N, it should not matter. So, n plus how many points are there in DFT? No, in DFT 9. So, 9i, where I is an integer. Okay? This is needed. If you ignore this, then you will run into problem. You cannot compute all the x 0 n's, and it is 0 otherwise. In other words, x 0 n is equal to, you see, in this summation I shall have only r equal to n and r equal to n plus 9i, other terms will vanish. If I put n equal to 0, then r equal to 0, which means x of 0, this 9 and 9 they take care, they cancel each other, x 0, then in the summation shall I have another term, x of 9, that is correct. This is for n equal to 0. For n equal to 1, I shall have x of 1 plus x of 10, very good, n equal to 1. Then x of 2 plus x of 11, n equal to 2, and then I do not have an x of 12, and therefore this will be x of n greater than equal to 3. All right, 3 less than equal to n less than equal to 11. That is right. This is the total solution. The point to recognize here is that r can exceed n by 9, 18, 27 and so on and so forth, so within the range of.
I should be positive in case of n is equal to 11 or n is equal to 10.
I should be, because x of n does not exist for n less than 0.
No, so for n is equal to 10.
For n is equal to 10.
So it could be x1 of and x1 plus x 10.
For n is equal to 10,
10 minus 9 1.
So 10
oh
minus
yes, okay, I is positive, yeah. I is an integer, is a positive integer, yes. It does not exist. You see, if you go from n equal to 0, you must stop at n equal to 11, right? You can't go beyond that. What you are saying is, suppose I have small n equal to 10,
1
then can I take 10 minus 9i? No, 10 already exists. Okay, 10 minus 9 is x of 1, which has already been taken care of. It will not come in this summation. But it is good to remember that small I should be greater than 0. You must confine to your, and in a sense this is overlapping, isn't it? This is aliasing.
So the next sample is this. Next samples.
Next sample, you see,
So
what
from
you,
0 to 11, it is
Yeah,
one sample.
yeah.
The previous is overlap. That's why x9 and x10 terms comes.
that's
And in
right.
the next, from 12 to
No,
12 to 20.
this is a 9-point DFT. So after 9 it shall repeat. If you want to find x0n by IDFT, by computing the program, then these points, I've made a mistake. What is the mistake? And we have continued with the mistake. Yes?
Up to 8 only.
Up to 8 only, it cannot go to, because you are computing, so that question will not arise. Okay? You are going up to 8, you cannot go up to 11, because x0n is an IDFT of 9 points. So we start with 0 up to 8. Very good. Good question. It brought out the important point. The next problem is 381. 381 says, let xk be the endpoint DFT of x of n, where capital N is even. Okay. Then it says define 2 n by 2 point, n by 2 length sequences Gn is equal to A1 x of 2n plus A2 x of 2n plus 1, Hn is equal to A3 x of 2n plus A4 x of 2n plus 1, where obviously n lies between 0 and n by 2 minus 1. Because there are 2n here, you can't exceed. The samples do not exist beyond these limits. Okay? Where it is given that A1, A4 is not equal to A2, A3. All right? So given a sequence x of n, you have taken the even numbered sequence, even numbered samples to form a sequence x of 2n, and odd numbered samples to form a sequence x of 2n plus 1, and then you make a linear combination in 2 ways, A1, A2, A3, A4. All right. So x of 2n, well, the g of n, how many points are there in g of n? N by 2 points, isn't that right? And h of n also has n by 2 points. So the next part of the, if you have understood this, then you understand the next part also. If g, k, h, k are the DFTs, n by 2 point DFTs, they have n by 2 samples, n by 2 point DFTs of g of n and h of n, find xk in terms of gk and hk. Now, is the problem understood? We have defined 2 capital N by, this is why capital N was even, 2 capital N by 2 point sequences by linear combinations of even numbered samples and odd numbered samples in 2 different ways, and we have taken the DFT of each. Can we find out the DFT of the original sequence, the mother sequence from which these 2 children are derived? Can we find out the DFT of that in terms of these 2 capital N by 2 point DFTs? That is the question. So, what the first thing we do, there are many ways of solving this problem. One of the ways is, first thing we do is we express x2n and x2n plus 1 in terms of g and h, and that is where this equation, this inequality is useful. In the denominator, you see it's a set of 2 linear equations. So, in the denominator we shall have a1 a4 minus a2 a3, that cannot be 0. If it is 0, then your solution breaks down. Okay. So, we solve for them and to bring variety into experience, this is something else that I want to point out. We will not compute DFTs, we will compute the Z transforms. Life becomes a little easier. Instead of writing e to the power minus j 2 pi n k by n and w capital N to the power n k, we have to remember that w is defined with a negative sign and so on. We will do with Z transform. Finally, we shall compute them on the unit circle, all right, with the required number of points. This is one way of solving problems, keeping the algebra a little more tractable. Because if you keep e to the power j 2 pi, and as I have been making mistakes, I always put n also, although specifically n has been k. If I make a mistake like this, then you are shattered. Okay, so we will work in terms of Z transforms. The solutions for x2n and x2n plus 1 from these 2 derived sequences, if I solve the 2 linear equations, that becomes a4 gn minus a2 hn divided by a1 a4 minus a2 a3 and minus a3 gn plus a1 hn divided by a1 a4 minus a2 a3. I have derived the 2 sequences in terms of G and H. I have inverted these relationships. Therefore, x of Z is equal to summation n equal to 0 to capital N minus 1 x of n Z to the minus n which I can write as, since I have derived 2 sequences, even numbered and odd numbered, I do them separately. X of 2n w, I do not want to use w, Z to the minus 2n, agreed, x of 2n Z to the minus 2n, where n goes from 0 to n by 2 minus 1 plus summation x of 2n plus 1 Z to the minus 2n plus 1 n equal to 0 to n by 2 minus 1. And then in these relations we substitute x2n and x2n plus 1. Then we bring in g, small g and small h. Is the point clear? We first solve for x2n and x2n plus 1 in terms of small g and small h. Then we write the Z transform, split it into 2 summations, one containing x2n, one containing x2n plus 1, and substitute for this. The result is the following: capital X of Z is equal to summation n equal to 0 to n by 2 minus 1 a4 gn minus a2 hn divided by A1 A4 minus A2 A3 z to the minus 2n plus ultimately we shall combine the two terms.
Yes.
Okay. So, instead of writing in the second one z to the minus 2n plus 1, I can take z inverse out, then I can combine the two summations. Okay. So, I take z inverse out and I write minus A3gn plus A1hn divided by A1 A4 minus A2 A3 z to the minus 2n. So, let us combine terms. This is equal to 1 by A1 A4. Now, I have got gn and hn. I want to compute capital X sub z. I have got gn and hn inside the summations, and now I have to put the g's together and h's together, and then put small z equal to e to the power j 2 pi divided by n by 2. All right, let us see. All right, we will put 2 pi by n. Because of this 2n, that 2 will come in the denominator. Is it clear? When you have written up to this, the solution should be clear. The rest is simply algebra. You see what we do. A1, A4 minus A2, A3. We take this out. Then I get A4, well, A4 minus A3 z inverse summation gn z to the minus 2n n equal to 0 to n by 2 minus 1. You see the summation limits are okay, n by 2 point has already come, and instead of z to the minus n I have z to the minus 2n, and therefore I have already got what I need to do, plus minus A2 plus A1 z inverse multiplied by summation n equal to 0 to n by 2 minus 1 hn z to the minus 2n. Okay. Now we put z equal to e to the power, we put z equal to e to the power j 2 pi k by n.
So n by 2
My capital X has to be computed with capital N number of points. So, if I put small z equal to, I have to put small z equal to e to the power j 2 pi k by n, because capital X has to be computed, whereas because of z to the minus 2 here, this will be automatically taken care of. This will be a summation over n by 2 point DFT. All right. So, I put this, then z squared is equal to e to the power j 2 pi k divided by n by 2. All right. Instead of 2 here, I have brought it in the denominator. Therefore, now I can write it w n to the power minus k w n. Now you have to bring the form, otherwise you cannot identify with the Fourier transform, and this will be w n by 2 to the power minus k, and therefore capital X sub z becomes equal to 1 by A1 A4 minus A2 A3 A4 minus A3, what shall I have here? Z inverse, that is W n raised to the power k, agreed. Then what do I have in this summation? What would be the summation? Capital G of k, right? I am not writing this summation again. Summation would be g of n w n by 2 to the power minus, not minus, plus, minus or plus. Let us write it down. Summation g of n w n by 2 raised to the power plus n k, where n goes from 0 to n by 2 minus 1. Then the second term plus minus a2 plus a1 z inverse, not z inverse, w n raised to the power k, summation n equal to 0 n by 2 minus 1 h of n w n by 2 to the power n k. And it is obvious that x of z, let me write it here, 1 by a1 a4 minus a2 a3 a4 minus a3 w n raised to the k g k plus minus a2 plus a1 w n raised to the k h k. That is not the complete story, because g k and h k exist only from 0 to capital N by 2 minus 1, whereas x k, I am sorry, this is, what did I call this? X, there is a problem here. In the formulation of the problem itself, we should have distinguished between them. Shall we, what should we do? Let us change our x of z. Let us keep x of k. Do you understand the difficulty? So let us call this x1 of z. The z transform we change to capital X1 of z. We can't use x of z and x of k both here. Okay. I have also made a mistake. I should have written this as x of k, right? Because z has been put equal to w n raised to the minus k. The z transform notation that I used, change that to some other symbol. Call it x1, x prime, or whatever you want. Now the story, as I said, this is not the complete story. This is only half of the story. We can compute gk and hk only from 0 to capital N by 2 minus 1, whereas xk has to be computed from 0 to capital N minus 1. So how do we do that? Okay, how do we do that? When small k exceeds capital N by 2, gk and hk, if small k here also exceeds capital N by 2, then since these are periodic, the values are known, and therefore we must put here gk modulo n by 2. That is it. Then you can go from k equal to 0 to capital N minus 1. Is this understood? Okay. The next one is also with a similar complication, 378. I will only solve the A part. It says consider x of n, a sequence x of n of length capital N, which is a DFT of capital X of k. All right. Then define a sequence y of n, which is the upsampled version of x of n, that is x of n by L, n equal to 0, L, 2L, n minus 1L. Why didn't you take plus minus? Because x of n is one side, it's a finite series, finite sequence one sided, starts at 0, ends at capital N minus 1 and is 0 otherwise, upsampled version. But y of n is now of length capital N multiplied by L, y of n of length capital NL, L being a positive integer. So far so good. We had capital N number of points in x of n, so when we upsample it, we are adding n minus 1 zeros in between, so the total length of y of n becomes capital NL. The point, the question is, express the NL point DFT of yn, that is capital Y of k, in terms of x of k. That is the question. All right. You have to take the NL point DFT of y of n, there are NL points, and see whether it can be expressed in terms of x of k. Now, we start from the definition of y of n, that is, we start from the definition of the DFT yk is equal to summation yn w nl, NL point raised to the power nk, where small n is 0 to NL minus 1, right. And this becomes equal to summation, but yn is x of n by L, where now n is 0, L, 2L, no plus minus, n minus 1 L, W. Does this change? No, that is important to recognize, W n L raised to the nk. All right. This factor remains the same. We are only substituting for y of n. We have not substituted, we have not changed n. We have only substituted for y of n. And to indicate that y of n, this exists only for integer arguments, we have included 0 L. We have not changed, we have not said n equal to 0 to NL minus 1, no. And this exists only at 0, L, 2L and so on. Now, we change n by L, we make n by L equal to R, x of R. Then R should go from 0 to n minus 1, agreed? N by L is equal to R, so R is 0, 1 up to n minus 1. Then XR W n L raised to the power R L K. That is equal to summation R equal to 0 to L n minus 1 x of R. Now, W n L is e to the power minus j 2 pi by NL, then R L K. So, L and L cancel, and isn't this precisely xk? But there is a problem. Do not leave it here, because yk exists from k equal to 0 to capital NL minus 1, whereas xk exists only from 0 to n minus 1. So, it has to be modulo n. Is that okay? Xk will repeat, and yk, the DFT of yk up to capital N points, it is identical with this, then it shall repeat. How many times? L times. Okay, very good. The next question, 374a. Once again I am solving only the A part, B part is the negative of this. It says let capital X of e to the j omega be equal to the Fourier transform of the sequence 1 1 1, where this is n equal to 0 and this is n equal to 7. In other words, it is a 8 point and its Fourier transform is capital X of e to the j omega. Now a cute thing is done, that is capital X of e to the j omega is taken and sampled at 10 points, In other words, x1k is obtained from capital X of e to the j omega by putting omega equal to, yes, 2 pi 10 point 2 pi k by 10. x1k is obtained. Okay. The number of points here is 8 and the number of points at which the DFT is computed is 10. All right. If they are identical, we had no problems, but they are different. We want to see what is the effect of this. The question is x1k is obtained by sampling capital X of e to the j omega at intervals of, no, the number of points is not given, it says at intervals of pi by 5, which means the number of points is, because 2 pi divided by pi by 5 is 10, all right. Starting from omega equal to 0, determine the IDFT of x1 of k. Determine IDFT of x1 of k, call this x1 of n, without computing, that is the restriction, without computing x of e to the j omega and x1 of k, none of this, you are only given x. So, in other words, you have to find x1 of n from x of n, all right. You have to find the relationship between x1 of n and x of n without explicitly computing the Fourier transform or the discrete Fourier transform. That is the question. And then there is an appendage, can you recover x of n from x1 of n? You find x1 of n, then can you recover the original sequence from this? That is the question. The answer in this case is yes, but the answer in B is no, all right. The B part, which I am not I have given the answer in the answer sheet. Now let us see how do we proceed. We start from x of e to the j omega, that is equal to summation x of n e to the minus j omega n, n equal to 0 to 7. 8 points are given, n equal to 0 to 7. And x1 of k is equal to summation n equal to 0 to 7 x of n e to the, omega is taken as 2 pi k by 10. So, it is minus 2 pi n k divided by 10. All right. This is what is given. This is sampled at 10 number of points. Pardon me? J. J was missing. Yes. Okay. E to the minus j 2 pi n k by 10. Is minus sign okay? Yes. We have not gone to Wn. Okay. Now we can't compute this or this. So what we will do is we will invert it. x of n. This is the standard trick. If you are not allowed to compute this, you invert this. So, you get 1 by 10, right, k equal to 0 to 9 x 1 of k e to the power j 2 pi n k divided by 10, and do the standard trick, that is replace x 1 of k by this, but you can't use the same variable, you have to change the variable. I want this to be a part of your heart so that you know what to do. Whenever there is a question of double summation, you must change one of the variables. So, I get 1 over 10 summation k equal to 0 to 9, then summation r equal to 0 to 7 x of r e to the power minus j 2 pi r k by 10 multiplied by e to the j 2 pi n k by 10. All right. If you want, you can put this in bracket. Then you interchange the two summations. K and r are independent dummy variables. So, you interchange the summations, and what you get is x 1 of n as equal to 1 over 10 summation r equal to 0 to 7 x of r summation k equal to 0 to 9 e to the power j 2 pi n minus r k divided by 10, and you look at this again. You look at this again. This would be equal to 10 for r equal to n or n plus 10 I. I is an integer, okay. It is 0 otherwise, positive integer, yes. And therefore, you can write this as, if it is 10, 10 and 10 will cancel. You can write this as summation r equal to, in general, minus infinity to plus infinity. Why do I bring minus infinity to plus infinity? X 1 of n is the result of an IDFT, and therefore, it will repeat, but it suffices to calculate how many points? 10 points. I have to calculate the first 10 points. So, for the first 10 points, in general it is x of n plus 10 r.
Sir, only 8 points. Sir, other
8 point was x of n, but capital X 1 of k is computed at 10 points.
So this will be computing.
We will have to find 10 points. Well, let us not bother about this. Let us see what are these 10 points. X 1 of n, when n equal to 0, it is 1, n equal to 1, it is 1, and goes on. N equal to 8, 1, not 8, 7. Up to 7 it exists.
Yes.
Then you have to go to 8 and 9. N equal to 8,
8 would be added to 3.
not added. You see, the original sequence was 8 point,
Yes.
and you have to now compute 10 points. So, what would be the other two? 0, 0. There is no aliasing here. Aliasing will occur if the number of points at which the DFT is computed is less than the number of points in the original sample. So, you know the answer, that it x of n can be recovered from x 1 of n. Is this clear? From the Z transform, if you go to the DFT with a larger number of points, there is no problem. Zero padding has occurred. If you go to a smaller number of points, then aliasing shall occur in the time domain. Okay? All right. We have a few minutes, we can do a couple of other problems. 368. It's a problem in similar lines. DFT is such a versatile instrument at the hand of DSP designers that uses DFT wherever possible, and therefore all kinds of problems arise. Now look at this. Let x of n and capital X of k be n point pairs in DFT, and n is divisible by 4 by 4. Let y of n be equal to x of 4n. This is a decimator. That is, you ignore the intermediate 3 samples. You take x of 0, x of 4, x of, and that is it. You construct a new sequence, x of 4n, where obviously the length now shall be reduced by a factor of 4. So 0 less than equal to n less than equal to n by 4 minus 1. That is why n was divisible by 4. Okay? The question is to express the n by 4 point DFT yk in terms of xk. Okay? The number of points at which the DFT is taken is less than the number of points in x of n. All right? So there shall be aliasing, there shall be additions of other things. Let us see how to solve this.
Why there will be aliasing? Because we have to yn is of length n by 4 and we have to compute n by 4 point DFT.
Yes.
Then why it is aliasing? We have already taken the compressed sequence. Then there will be no aliasing between yn and yk. We can obtain yk, yn again from yn.
Yn again from?
Yk.
No, yn can always be computed from yk. Can you compute xn from yk? That is the point. Right? That cannot be done. Okay. So my yk by definition is n equal to 0 to capital N by 4 minus 1 yn w of n by 4 raised to the power nk. And I substitute for y of n. Now we do not have to restrict n. Now y of n is x of 4n. Unlike upsampler where there was a division, there is no problem here. N is an integer, 4n is also an integer. Okay. So n equal to 0 to n by 4 minus 1 w n by 4 raised to the power nk. So x of 4n, now here is a twist. X of 4n we will compute in terms of capital X of k. You see what the problem now is? Problem is to express yk in terms of capital X of k. Now we have expressed yk in terms of x of 4n. From x of 4n, let us bring capital X of k. That is relationship between capital X of k and small x of 4n. If we substitute that, then we shall get yk in terms of capital X of k. So I substitute x of 4n, I compute by inverting capital X of k. So it would be 1 by n summation let us change the variable, m equal to 0 to n minus 1 capital X of m w n raised to the power plus or minus 4 n m k. Oh, 4 n k. N m. Okay. I always seem to make a mistake here. Let me write it again. X of 4n is equal to 1 over n summation m equal to 0 to n minus 1 capital X of n w n raised to the power minus 4 m n. Have I done it correctly now? Good. Now this 4 I can bring here. Okay, so I can write this is 1 over m equal to 0 to capital N minus 1 x of m w n by 4 raised to the power minus m n. And I now substitute this, substitute x of 4n, I substitute this here. I get a double summation and we apply the same trick, that is interchange the summations. Okay, let me write it down. I therefore have yk as equal to 1 by n summation after the interchange m equal to 0 to n minus 1, then x of m summation n equal to 0 to n by 4 minus 1 w of n by 4, this is why I converted to w of n by 4, okay, to the power n into k minus m, and this now is equal to capital N, capital N, n by 4, the number of terms is n by 4, for m equal to
n plus small n plus
k plus n by 4.
say it again, k plus n by 4 multiplied by some integer r, okay, I, okay, I. We have used I earlier, we must be consistent, okay, times I, otherwise it is 0, and therefore I get 1 by 4, yes, because n by 4 and 1 by n, so 1 by 4 comes in the denominator, then m equal to 0 obviously shall come, so x of k, now wait a second, that is right, x of k, because m equal to k plus n by 4i, so x of k comes. In this summation only a few values of m shall figure, okay. So the first one will be x of k, second one would be x of k plus n by 4. Why is this required? Because x of k is computed only from 0 to n minus 1. Whereas yk is required, I am sorry, yk is required only for k equal to 0 to n by 4 minus 1, okay. So xk is okay, then xk plus n by 4, how many such? another 2 terms, x plus 2n by 4 plus x k plus 3n by 4. Why do we end here? Because the next one is simply xk, it is periodic. Therefore, yk becomes a sum of several versions of capital X of k. All right? I think I am right. I think I have not missed anything. The last problem. 1227, yes. The last problem is 357. It is a tricky problem, but the solution is very simple. It says even samples of 11-point DFT, of the 11-point DFT of a length 11 real sequence are x of 4 is equal to 2 plus j5, x of 0 is equal to 4, x of 2 is equal to minus 1 plus j3, x of 4 is this, x of 6 is 9 minus j6, x of 8 is equal to minus 5 minus j8, and x of 10 is equal to root 3 minus j2. It simply says determine the missing odd samples. Nothing else is given. Determine the missing odd samples. If you want to do it mechanically, you see, I need 11 samples, 11 point, okay. Only the even numbered ones are given. How many? 1, 2, 3, 4, 5, 6. 6 of them are given. The remaining 5 have to be found out. If you want to do it mechanically, then you shall write x of 0 as summation x of n equal to 0 to 11, and write the next equation, and try to solve them to find out x of n. Well, that is mechanical, and you will make your life miserable and extendable to any limits of fatigue. Whereas, we know that for a real sequence, now these tables come into effect. For a real sequence, xk is x star minus k modulo n. So, x of 1, for example, would be x star of 10, and x of 10 I know, so x star of 10 would be root 3 plus j2. Okay? This is where use of the tables come. Otherwise, if you want to do it mechanically, as I said, you will make your life miserable. We will stop recording at this point.